Happy morning. This is Morgan, Assistant Professor, Department of Agriculture Engineering. Today I'm going to discuss about the most economical sections in Open Channel. So we have a four different type of channels are there. One is rectangular section, triangular section, trapezoidal and circular sections. In this, which sections which has the maximum discharge, that we can say that is a hydraulic efficient channel, a channel which gives maximum discharge for a given cross-sectional area and bed slope. So it's called hydraulic efficient channel, or otherwise called as most economical section. So now we will see one by one the most economical section for rectangular. When this rectangular channel, trapezoidal, circular as well as a triangular channel will become more efficient, that is it will give maximum discharge with respect to the cross-sectional area and bed slope. Let me go with the first one is about most economical section for rectangular. So the figure shows that the rectangular sections. So this is the breadth of the section and this is my depth. So area for rectangular section is BD and we have the perimeter. The perimeter is B plus 2D. The vectored perimeter is B plus 2D, that is water touched portions in the rectangular section is, or in any section is a perimeter. So this is B, the water enter into this channels through this D, B, D. Oh, we are adding all this dimension B, D plus B plus D, so B plus 2D. So area is equal to BD. So let me, from this area we have a B is equal to A by D. Substitute this value of B in equation number 1. So where P is equal to B can be replaced by A by D plus 2D. So I am differentiating this perimeter with respect to depth D. So dP by dd is equal to A by D. When I am differentiating this A by D with respect to D, so I will get minus A by D square plus 2D. I am differentiating 2D with respect to D, I am get 2. So dP by dd is equal to minus A by D square plus 2 is equal to 0. So the vectored perimeter should be minimized and equating to 0. So from this A minus A by D square plus 2 is equal to 0. So the equations will become minus A by D square, okay, minus A by D square plus 2 is equal to 0. So minus A by D square is equal to minus 2, minus minus getting cancelled. So from this A is equal to 2D square. This is the area in terms of depth. From this equations we know that B is equal to A by D. A is nothing but 2D square. So 2D square by D. So where B is equal to 2D. DD getting cancelled, the B will become 2D. And we have a hydraulic mean depth. M is equal to A by P, where A is area, P is perimeter. Area we can get as 2D square, and the perimeter is B plus 2D. The B value is 2D. So 2D plus 2D. So the numerator 2D square, the denominator 4D. So 2 getting cancelled. So 1 by 2 times of D, that is M is equal to D by 2. The channel, the rectangular channel becomes most economical through which we can able to get maximum discharge if the breadth is equal to 2 times of depth and M is equal to D by 2. With these conditions are satisfied, the channel can gives the maximum discharge with respect to this dimensions. So next we'll move on to most economical section for trapezoidal. Here it's all the same conditions. We have the perimeter. So perimeter for the trapezoidal section is where perimeter P is equal to B plus 2D into square root of 1 square plus n square, that is 1 plus n square. N is side slope of the trapezoidal section and area is B plus nd into D, that is BD plus ND square. The term B is also a variable on the vectored perimeter because bottom width having B and top width is having B plus 2ND. So B is a variable parameter in this trapezoidal section. So from this B is equal to A minus ND square by D. So A by D minus ND. This is in terms of B. So substitute the value of B in perimeter where P is equal to A by D minus ND plus 2D into square root of 1 plus n square. To make the trapezoidal section most economical, the vectored perimeter is minimized. To make the trapezoidal section most economical, the vectored perimeter is to be minimized. So I am differentiating the perimeter with respect to D. So dP by dd, that is equal to minus A by D square minus n plus 2 times of n square plus 1. that is equal to 0. When I'm equating to 0, we may get the value a plus n d square by d is equal to 2d plus 2d into square root of 1 plus n square. So we have the value of a is equal to b plus nd into d. This is the formula for area. When I'm substituting this in the equation number 3, so a is bd plus nd square by d is equal to 2d into square root of 1 plus n square. So bd nd square 2 nd square divided by d, here is 2. So bd plus nd square 2 nd square. I'm taking d is outside. Here is denominator is also d, numerator is also d. So dd getting cancelled. So b plus 2 nd by 2 is equal to d into square root of 1 plus n square. So the equations will become half of top width, that is 1 by 2 times of b plus 2 nd is equal to 1 of side slopes, d into square root of 1 plus n square. So let we have the hydraulic mean depth where m is equal to a by p. A is b plus nd into d divided by the perimeter is b plus 2d into square root of 1 plus n square. When I'm substituting the value of d into square root, that is one side of side slope is half of top width. So b plus 2nd by 2 by 2 in terms of d into square root of 1 plus n square. I'm equating all these things. I'm get the main hydraulic depth is d by 2. So if the dimension is d by 2, hydraulic mean depth is d by 2, the section will give the maximum discharge. So that section of hydraulic efficient channel for trapezoidal section is m is equal to d by 2. The hydraulic efficient channel for trapezoidal section for getting the value of the side slope n. So we know that the b is equal to a by d minus nd, and the perimeter equations and area equations we already knows. We are to get the best side slope. I'm going to differentiating the perimeter with respect to n and keeping a and d as a constant, because I'm going to get the value of side slope. What will be the maximum side slope through which we can get the maximum discharge? When I'm differentiating the perimeter with respect to n, I'm keeping my a and d are constant. I can get the value of n. The side slope n is equal to 1 by square root of 3, through which tan theta is equal to 1 by n, where n is equal to 1 by tan theta, that is cot theta. Cot inverse of 1 by root 3, n value is 1 by root 3. Cot inverse of 1 by root 3 is equal to theta, where theta is equal to 60 degree. When we get the maximum discharge in case of trapezoidal section, the best side slope in trapezoidal section must be adopted in practical situation is about 60 degree. And most economical section for circular. In circular, there are two conditions that we have adopted. One is depth of flows below the center of channel. The second one is depth of flows above the center of channel. The vectored perimeter with respect to circular channel, where perimeter is equal to 2r theta, cross-sectional areas r square into theta minus sine 2 theta by 2. This is for the perimeter and area for circular section. If the condition is the depth of flow d is below the center of channel. So second one is depth of flows above the center of channel. The perimeter is same for both the cases, but area r square into theta minus sine 2 theta by 2. So area and perimeter is constant for both the cases, but only the condition is the depth is above and below the center of channel. Depend upon the center of channel and depth of flow, it's getting varied. So the circular channel with maximum, where area is equal to r square into theta minus sine 2 theta by 2, and we have the perimeter is 2r theta. We know that the discharge equation with respect to chassis, where q is equal to ac into square root of mi. M is a by p. When I'm AC into square root of a by p into I. When I'm substituting a in terms of square root, we can get c is equal to, c into square root of a cube by p into I. When I'm getting the maximum discharge, I have to differentiating this equations with respect to theta. So d by d theta of a cube by p. So it is in the Bernoulli's equations. As per Bernoulli's equations, uv dash minus vu dash by u square. D by d theta of a cube by p, that is a cube is u, p is v. So u v dash minus v u dash divided by v square. So 3a cube into dA by d theta minus a cube into dp by d theta divided by p square. So 3p a square a cube. So when I'm taking a square is outside and equating to 0. So 3p dA by d theta minus A into dP by d theta is equal to 0. So when I'm getting equating all these cases, when I'm getting the theta is equal to 2.69 radians. When I'm substituting in this equation where depth of flow is equal to radius minus r into cos theta, where r into 1 minus cos theta, when I'm substituting the value of 2.69 radian, I may get the d value of 1.9 times of r. So radius is equal to diameter by 2. So we get discharge when depth of flow is equal to 0.95 times of the diameter of the channel. So when I'm getting the maximum discharge in circular channel, the depth of flows, maximum discharge is obtained when the depth of flow is 0.95 times the diameter of the channel. Likewise, a circular channel with a maximum velocity, the circular channel with the maximum velocity, we may get the radiant is 2.25. When I'm substituting the theta value is 2.25 radian, we may get the value of d is equal to 0.81 times of diameter. When I'm getting the maximum velocity which is flowing inside the circular channel, when the depth of flow is 0.81 times the diameter of the channel. This is for triangular channel for the best hydraulic section. In the triangular channel, we have the most economical section for triangular section is where m is equal to d by 2 square root 2. And theta must be the maximum side slopes for the triangular section. It should be adapted for getting the maximum discharge is about 45 degree. From this we can get the m, mean hydraulic depth, is equal to d by 2 square root 2. And the most economical section, the reason for using the Manning's formula, because in open channel we are using two different type of equations for calculating the discharge. One is chassis, another one is about Manning's. Manning's is most suitable for open channel if it is in by natural path. So reason for using Manning's formula, standard tables have been proposed to find out the roughness coefficient based on the factor which depends upon roughness of the surface, irregularity of the cross section, vegetation, irregularity alignment. With respect to this 4 factor, we have the value of n as per the chart. So through which Manning's roughness coefficients can be used in all type of open channels. The limitations where we have not used this Manning's formula. Manning's formulas cannot be used for laminar flow because it's completely open and turbulent in nature. Always the open channel must be in turbulence in nature. So in case of laminar flow, we couldn't use this Manning's constant. There we can use chassis constant. And hydraulic efficient channel for calculating the discharge in terms of Manning's, where Q is equal to 1 by n A m power 2 by 3 I power of that Z by n by I power of that Z is equal to A m 2 by 3 is called as section factor. And we have the normal depth. So from this normal depth is A m power 2 by 3 is equal to Qn by I power of. It is required to calculate the normal depth. The normal depth is for the given discharge is Y. So thank you. We will discuss the remaining part of open channel in the upcoming sessions.